Hello everyone, we are the Phoenix Energy Technology Capstone team at UCI. The members of our team include myself, Emily Welch, Zemin Me, and Shema Abdasami. We are all aware of the impact of global warming and the need to reduce our emissions. One way we can do this is by reducing the total amount of energy demand, but also to choose when to use this power. At peak periods of the day when demand is high, utility companies charge more to encourage customers to use less. HVAC systems account for about 50% of a building's total energy consumption, which is why our team has developed a tool that will optimize HVAC set points to minimize the amount of energy needed and to prioritize when it is used. We've created a tool that will estimate from these optimized set points the energy and financial savings for a retail space in Los Angeles County that can be adapted for other locations.
HVAC conventional control logic only considers static parameters like indoor temperature and air quality. Our team is building an autonomous, artificial intelligence-based system that optimizes a building's HVAC set point every 15 minutes by evaluating dynamic parameters such as weather, time of day, occupancy. Our solution is expected to deliver significant energy savings while decreasing a building's carbon footprint. We have broken our solution into two phases. Phase 1 is creating a building model using building information such as geometry, materials, weather data, occupancy, and CO2 levels. We used Energy Plus, a building simulation software, to simulate the building energy consumption baseline. We then applied different ECM strategies such as pre-cooling, demand control ventilation, and economizer operation. We ran Energy Plus to obtain the potential savings on energy consumption. We then assumed a tariff structure based on SoCal Edison rates to determine prospect savings.
We first used 4 months training data, which including the building's conditions like occupancy and weather, to train the machine learning model. After the model is trained, we can output the optimized set points using this model and input that into the Energy Plus simulation. The Energy Plus simulation will use tariff engine and these set points to output the saving on the energy cost.
Phase 1. Energy Plus Building Simulations.
Our building prototype was based on Department of Energy simulation program. The program modeled 16 commercial building types in 19 climate locations. The program covers 80% of the commercial buildings in the USA. We use standalone retail model, which represents majority of Phoenix client base. We used the following assumptions to create our building model. A single-story standalone retail building with a total built-up area of 24,700 square feet. The cooling system is packaged rooftop air conditioners. Heating system is gas furnace. Location and weather files are in Los Angeles County. We use Title 24 2008 Energy Code, and the building vintage is 2008. Our next step was to apply energy conservation measures, ECMs. Our first ECM was deploying economizers. When outdoor temperatures are low enough to cool the building, outdoor air is drawn into the building using economizers. This strategy resulted in reducing 4.5% on cooling loads. However, it did not show significant reduction in total energy consumption. Our second strategy was demand control ventilation. This strategy resulted in 6.9% reduction in overall energy consumption. Our final strategy was pre-cooling. We reduced the cooling set point 4 hours before peak demand period and allowed the set point to float during peak demand period. This strategy resulted in 8% reduction in overall building energy consumption.
Phase 2. Machine Learning.
Here is the machine learning results. The input of the machine learning include the store hours, the occupancy, which is estimated, temperature, and humidity. On the graph in the right side, we can see the relationship, the distribution of the inputs with the set points. The machine learning model shows validations of the LM algorithms by the low arrow, which is down to 0.7 degrees, compared to the linear model and temperature domain model, which are each 1.6 degree and 2.2 degree. The model is really effective, and it takes only a few minutes to generate the set points for the entire year. Based on the other research paper we investigate on building temperature monitoring, the average arrow is just 0.5 degrees, so we believe our result is relatively reliable based on the data set we get.
August 15th, 2021 was a warm summer weekend in Los Angeles County, a perfect day to demonstrate energy savings in an HVAC system. The left graph shows the estimated energy profile comparing baseline, pre-cooling, and our generated optimized set points, while the right graph shows when financial savings start to diverge between the scenarios. On just this one day, we were able to generate savings of 72 kilowatt hours and over $11. The retail store that we trained our models on spends an average $21,100 annually on their HVAC system. By employing a pre-cooling scenario, the store could save an estimated $885 annually. But if we employ our optimized set points that were derived from our machine learning, we can estimate savings of over $1,000. We have created and analyzed the effect of 5 different scenarios a building can implement by creating an optimized baseline, altering the performance of the economizers and DCV, by employing pre-cooling, and by generating an optimized schedule using a combination of baseline and pre-cooling schedules. We have employed machine learning and simulation tools to reduce energy consumption and entice users by boasting financial savings of a significant 5%. If more retail spaces employed these techniques, we could have a greener future. Thank you.